Well, thank you all for coming. Our speaker today is Professor Alexander Wyglinski from Worcester Polytechnic. Alex is an expert in the field of wireless communications, specializing in cognitive and software-defined radio, dynamic spectrum access, cyber-physical systems and security, and wireless system optimization and adaptation. He is an associate professor of electrical and computer engineering at Worcester Polytechnic Institute in Worcester, Massachusetts, director of the Wireless Innovation Laboratory, and the lead investigator of the Cyber Physical and Secure Systems Initiative at WPI. Alex received his bachelor's in engineering and PhD degrees in 1999 and 2005 from McGill, and his master's in engineering from Queen's University in Kingston in 2000, all in UWEE. Throughout his academic career, Dr. Wyglinski has published over 30 journal papers, over 75 conference papers, 9 book chapters, and 2 textbooks. One of them just came out a few months ago. His research activities have been or are currently being sponsored by DARPA, the Office of Naval Research, the Naval Research Laboratory, the Air Force Research Laboratory, MathWorks, MATLAB, Toyota Infotechnology Center, and the National Science Foundation. He's a senior member of the IEEE, as well as a member of Sigma Psi, Eta Kappa Nu, and ASEE. And on a more personal note, Alex has been the driving force behind revamping W420 here in the department, the capstone design course in communications, through significant input from him over the past few months, and a recently published book on software-defined radio. Please join me in welcoming Alex. Thank you.
Well, thank you very much, Professor Arab Sahi, for your kind introduction, as well as this invitation for me to present to UWEE today. So, and good morning to all of you, and or for me, it's more like good afternoon. So I think I'm well aligned in terms of, sort of like my alertness level. So thank you again. It's a pleasure to be here in Seattle and giving some sort of, a talk on some of the research activities that I'm pursuing at Worcester Polytechnic Institute, or WPI, all focusing on software-defined radio, which is essentially is a paradigm shift in the way we do communications from the 1980s and 1990s, and because of the latest advent in the computer technology, we're able to truly leverage this the latest in microprocessor systems, processing power and stuff, to do communications in ways that were not even realizable over a decade ago. Okay. So my talk, I'm first going to give an introduction to myself, what is software-defined radio, what's cognitive radio. I'll then give a history lesson. So perfect on a Tuesday morning, a little bit of a history class. I'll then talk a little bit about my lab, what we do, who's sponsoring us, and then I'm going to focus on 2 of the several research activities that I'm conducting at WPI. And then following that, some concluding remarks and some more information. All right? Okay. So first of all, who I am. So that was a photograph of me when I just started WPI in 2007 as assistant professor. Since then, things have changed, including some recent style changes. But I'm currently an associate professor at WPI in the electrical and computer engineering department, receiving tenure last year, and I started there in 2007. Before that, I was at the University of Kansas as research faculty and was working on actually a major project that was sponsored by DARPA and the NSF, involving the construction of a rather versatile software-defined radio platform. So that's where I got my start in this domain. As Professor Arab Sahi described, I got my PhD degree from McGill on a more fundamental concept involving optimization of wireless local area networks and multi-carrier modulation. And it was a great mix where I took sort of the aspects of optimization and adaptation and then combined it with programmable hardware to create a lot of research in the way of software-defined radio and this thing called cognitive radio, which I'll describe in a few minutes. Some of the other things I'm active in, a distinguished lecturer in the IEEE Vehicular Technology Society for the next 2 years, as well as an editor for the Communications Magazine and IEEE Transaction Wireless Communication. So 2 sort of major publications in the Communications Society for IEEE. I'm also, if any of you are interested in presenting work in sort of the mobile wireless domain, there is VTC 2015 in Boston, which I'll be co-chairing. Boston's a great place. Chowder's awesome. Please come. And in terms of publication, published extensively in this area, and as well as federal and industry grants supporting it. So I mentioned this word cognitive radio. And whenever I mention the word cognitive and then I encounter, let's say, a psychologist, they're like, oh, cognitive, and then no, different cognitive, okay? So cognitive radio is the result of taking, let's say, several different areas, not only in electrical and computer engineering, but also from areas like economics, like psychology, and mathematics and computer science, and then couple it with a very agile platform, okay? In this case, a software-defined radio, to do things in an automated fashion, an intelligent manner, without any human involvement, all right? If you go to Wikipedia, which is always a very reliable source of information, just kidding. What is a cognitive radio? What's the definition that they give, okay? So one definition is cognitive radio is a kind of two-way radio that automatically changes its transmission and reception parameters in such a way that the wireless communication network, of which it's a node, communicates efficiently while avoiding interference with licensed or unlicensed users. In other words, you have a radio that automatically takes care of a situation for you in the sense of, oh, I want to transmit in this part of this frequency band, but I don't want to interfere with anyone else. And maybe at the same time, I want to optimize my radio to get the most information across that channel while minimizing, let's say, my power consumption. I have a very low battery life right now on my platform. Let's say there's it's not plugged into a wall or anything. Oh, and by the way, there's like 5 other radios communicating in the same vicinity as me, both in terms of frequency and geographically. So the radio, instead of having, let's say, a human operator tweedle some knobs and such and trying to sort of sound out the best configuration, the radio will sense the environment around it and then say, okay, based on these parameters, I believe that this is the configuration I should use in order to achieve my objectives, okay? And that's where the cognitive part, it's a cool buzzword, but it implies that there's some sort of onboard intelligence that's driving this platform, okay? There's another definition. So some folks and friends of mine at Virginia Tech, usually the sort of much simpler definition is it's a software-defined radio with a cognitive engine brain, okay? So there's some sort of software that's running in real time, collecting stimuli around the environment, and then it synthesizes it and says, okay, based on what I see around me, I'm going to do this, right? And under a certain, let's say, number of constraints and operating conditions. So cognitive radio essentially, and I have a great block diagram that illustrates this, essentially takes all these stimuli, takes all these constraints and all these available configurations and makes a best decision. And all of that is related through things like mathematical equations, right? Cost functions, optimization theory, which makes a good chunk of this area. So cognitive radio means a lot of things to a lot of people, okay? So cognitive radio, I mentioned the word intelligence a lot. I didn't mention the word agile, but that's also a factor. I deal a lot with what we call spectrally agile waveforms. How do I transmit in the presence of, let's say, several other users who are maybe not so agile? I sort of wrap my signal around them, avoid interference with them, but still get my 10 to 20 megabits per second data rate right across that channel. So there are a variety of other things like adaptation, opportunistic, seeking out opportunities that might not be available to a conventional radio. Dynamic spectrum access, that's something that's quite big out there. Optimization, I mentioned. Learning. Learning is the one thing that you don't see much in cognitive radio. It's not like, things like optimization and agility and environmental awareness. This comes up a lot in the community. Learning is the one tricky thing that we're still trying to wrap our mind around. And in fact, that's where some people say, you have cognitive radio, which should have learning. And learning now really involves psychology, especially if you have a human user of that radio. How does the radio know that this configuration is optimal for you? Let's say the radio is picking up video. How does the radio know that the video it's receiving is of great quality to the human user, right? And that's actually kind of tricky because now we're getting into the mind. What does the human mind perceive as the video transmission being of sufficient quality or audio quality, right? It can be related by an SNR, Sometimes, but maybe not always. There's not usually a linear relationship between the two. And then what happens if it's not of sufficient quality? How does the radio learn from its experiences to say, okay, I need to do this to get an even better performance for my human operator? Okay. So cognitive radio, these are some of the terms that are thrown out there. A lot of folks that, let's say, deal with radio platforms that don't have an element of learning sometimes call it agile radio, right? So cognitive implies, like cognition, like learning and adaptation and reaction. But an agile radio does all of that, maybe removing the learning aspect. Maybe you put some sort of automation or adaptation into it. Okay. So now here's the history lesson. Okay. So now I'm just going to see everyone get comfortable and no, just kidding. This is actually fun. When I applied to McGill for my undergrad, the two choices of programs were electrical engineering and history, because I do find it fascinating. And it's nice to see where we come from because of several reasons. First of all, you get a better appreciation of what we have now compared to a century ago. And the second thing is history tends to repeat itself. What is old is new again, right? So I've noticed in about ECE, every 20 years, it's like, hey, how about interference alignment? Yeah, they talked about that about 20 years ago with DSL modems and such, right? And then now let's do it for wireless, and we have all this great technology. So it's almost like there's almost like a cycle, if you will, and it's tied very closely to technology. But where did this technology come from? Okay, so again, I'm going to turn back to Wikipedia. So you might think when you think of communications, right? First person you probably think of, or maybe not the first person, but one of the people you think of is Marconi, right? And so he came up with wireless transmission. He was able to send messages across the Atlantic between Newfoundland, Signal Hill, and out in the United Kingdom, right? To sort of prove that you can communicate between points A and B wirelessly by exciting having some sort of electromagnetic wave or propagation or signal that's somehow its physical parameters, could be amplitude, could be phase, could be frequency, is changed over time to convey some sort of meaningful information, right? The next guy, really, really important guy. It was very unfortunate that when he passed away in this millennium, it's maybe there was a little bit of news, but this guy was huge in our area. He established the limits to which we can communicate information, digital information, reliably, okay? And with that bound, the Shannon capacity and many other things. This guy was extremely smart and had a lot of capabilities, including other things, lesser known interests like juggling robots. But for the most part, Shannon established a bound that then everybody proceeded to try and reach, all right? So you have Marconi, who was sort of the technology guy, and he's saying, okay, how do we get electromagnetic energy from point A to point B? You've got Shannon, who was okay, what are the fundamental limits of this technology in terms of communicating digital information? Now here's the third set of the part of the equation that people don't think when they think of communications. When I was an undergrad, I was in this stovepipe. It was called Communications and Signal Processing, and away I went, and I studied all about modulation scheme. I studied about filter design, but I didn't really focus too much on the computer engineering side of things. But in fact, nowadays, especially nowadays with the technology that we have, the transistor is extremely vital to modern communications technology. This thing that we call software-defined radio. This thing where what we've got is essentially all our algorithms are implemented on a microprocessor system or programmable logic and such. These guys, they came up with essentially, not only does it facilitate, let's say, us having our laptops open and checking email and really moving that information age forward, but at the same time, in terms of communication systems, especially from the 1980s onwards, essentially allowed us to explore new ways of communicating not even thought about before. Before, we had application-specific integrated circuits, or ASICs, which implemented one type of functionality, and that was it. And if you wanted to change that functionality, you've got to rip out the circuit, put in another one, or have multiple circuits, and then you multiplex them somehow in terms of operation. Now, if you don't like a certain radio configuration, delete, and then program a new one, right? Maybe not as as easy as that, but the general feeling, right? It's like it's all based on the same hardware, but it's programmable. So these sorts of innovators, and there are lots of them, you got to keep in mind that where we are today is the coupling of folks that look at broadcast and wireless technology, the people set the limits. You have also folks that do the computer engineering side of things. And what we've gone from are like from the days of, computers that fill whole rooms, right? Yeah, I have that in my living room. It's pretty cool. Down to essentially things like this beautiful Raspberry Pi here, which, is a great little platform. $25, you have all this microprocessor technology in your hand. You connect, let's say, an inexpensive, off-the-shelf wireless device, and you too, in a matter of an afternoon, can start, creating wireless platforms that do really cool stuff that, many years ago, you had to be a ham radio operator, and you know how to solder, and you know a little bit about RF and all that. So nowadays, we've gone from, let's say, these huge computing systems down to things that can fit in the palm of my hand, on the side of your belt, like your cell phones, like iPhone users, Android users, BlackBerry users, and such. Like, basically, we're surrounded by cheap, inexpensive, powerful microprocessor systems. And right now, communities like the wireless communications community are taking advantage of this, especially in things like, for instance, structural health monitoring using sensor networks. Imagine you have a tiny little computing device that makes decisions on, let's say, the strength of a bridge, and then it's wirelessly communicating that information to some central node saying, hey, I'm detecting some weird vibration here. Maybe you should get someone to check this bridge structure or whatnot. And this is just one of many examples. We're surrounded by microprocessor systems. A car alone has 150 computers in it, right? Power windows, power locks, your entertainment system, the fuel injection. I'm not sure. How many people here drive standard transmission still? Standard transmission drivers? Okay, handful. So everyone else is driving automatic. That stick is not really doing anything. Like, oh, I'm going to go into drive. It's just telling the computer, oh, yeah, okay, you better tell the automatic transmission to go into this mode, right? So in essence, what happens is we're basically, everything's, because of cost, because of the power of what these systems have to afford, we're more and more relying on computing systems. And what we see is that the general trend of communication systems over the decades has also sort of highlighted this. We've gone from, let's say, from the 1900s to the 1960s, hardware-based radios, like CB radios, like, basically application-specific, hard-coded type platforms. And then all of a sudden, when computer technology, so remember, the transistor was invented in the mid-1940s, and then it took a while before we began getting viable computing products out of it. And then in the 1960s, 1970s, we start getting what they call software-controlled radio systems, where what happens is, sure, you have hardware, but you have a computer that's sort of telling what the configuration of that hardware radio should be. And then we go one step further into the 1980s, where now computer technology has matured just a little bit more, such that now, okay, instead of controlling hardware, maybe we can define some of the processes of the radio itself, like modulation, like equalization, like filtering, on the microprocessor system itself. Then we go into the 2000s. And we talk about dynamic spectrum access radio. So now the radio does not just implement the functionality in software, but also now says, okay, here's a very unique situation. I want to transmit in this spectrum, but I know that there's somebody here who has exclusive rights to it, so I can't interfere with him. I have to readily change my configuration in 20 milliseconds, say. That's dynamic spectrum access radio, where the ability for the radio platform to reconfigure on the fly whenever it's experiencing like any sort of interference and it needs to get out. And then last but not least, cognitive radio. So we take it one step further. So it's not just only spectrum, but it could be a slew of other things. Like, let's say, opportunistically seeking out the best type of wireless access out there and in order to meet some sort of need. Oh, and by the way, your battery's low. Oh, by the way, the person has finished checking email and now is going on YouTube. So now my requirements for transmission have changed totally. So what we've seen is, with some delay, we've seen sort of a nice kind of bonding relationship between how computer technology matured, and then with a little bit of latency, communications technology sort of followed suit. So there is an actual relationship. It's not just by fluke that communications technology and the cell phones that are about paper thin that you can't even feel on the side of your belt have reached this far independent of computing technology. In fact, the two are coupled very closely together. Okay, so surveying, good that there's a big crowd because this will make it statistically accurate. Okay, so, and it's not for credit, okay? So how many of you own a cell phone? Okay, how many of you own a cell phone? Okay, and everyone else is like, oh, what's he asking? Okay, so I'm assuming almost everybody here has a cell phone. I thought I was a holdout in terms of not getting a cell phone until 2006, but I found someone actually just last year, he got his first cell phone. So how many of you have a laptop with Wi-Fi? Again, raise of hands. Okay, great. How many of you use an ATM? I hope so. It's like, hey, I need to go to McDonald's. I need to get a $20 bill or something like that. That, in a lot of cases, uses wireless technology. The first two are kind of obvious, right? Cellular, like we access it because of the wireless convenience that it offers. Same thing with the laptop. Checking your Facebook or Twitter account. Probably you're tweeting right now, oh, okay, there's this guy from WPI giving a talk, okay? And then the ATM is kind of interesting because what happens is sometimes ATMs are located in isolated locations, and then it might not be able to be accessed by a wired internet infrastructure. It might need some sort of wireless connectivity. Have any of you tried, this is Seattle, of course, so have any of you tried trying to fill your car with gas in a rainstorm? No? Okay. So what happens is, suppose you do, or if you watch satellite TV and all of a sudden there's a rainstorm. You sort of begin, the attenuation caused by the rain and the frequencies that, let's say, that ATM, that gas station, your satellite TV causes I'm not sure if this is the right term, rain fade. Essentially, it attenuates, it absorbs the energy, and it kills the signal, right? And so you might wonder, what are these questions as well as things like flying a plane, which I had kind of some experience with in the last 24 hours. What do they all have? Or even traveling in a car. All of these have computers and they have wireless, right? Whether you like it or not, the information, our sort of connection to society is all connected by the combination of a wireless technology and computing technology. For instance, cars. Like yesterday, I was at Toyota in Mountain View, California, and they're all about sort of the next generation. What's 10 years out? What will cars have? And then you also hear at the same time, oh yeah, cars are also going to be self-driving in 10 years, right? You already have states saying, oh, okay, we will permit autonomous vehicles on our road and such. That's going to be a lot of information, right? Imagine you have autonomous cars and you have human-operated cars. There's going to be a lot of exchange between, let's say this autonomous car wants to, cut off or go in front of a human-operated car. There's going to be a ton of information being shared between those two in order to perform that operation. Otherwise, bad things happen, right? So more and more, cars are being outfitted with wireless, more so than the OnStar and other sort of commercial products out there. Planes, definitely, like the avionics on the plane, the guidance, navigation. Now you have Wi-Fi on planes and such. So more and more, this wireless technology is in every aspect of our lives. And taking an example from the CTIA about cell phone usage, in 2008, in June 2008, the number of cell phone subscribers, this is any indication of how we bought into wireless technology, this convenience that's with us, reached 262 million subscribers. This is, although there's about more than 300 million Americans right now, this number is a little bit misleading because there are some folks that have 2 or 3 or 4 cell phones, right? So they almost look like a Jedi Knight. They have like 4 or 5 cell phones on their belt. But let's say we take those 262 million subscribers. How much time do you think they spent on the phone that year? 1.1 trillion minutes. So you can imagine the rollover, right? So not only is there a lot of cell phone users, there are a lot of cell phone users that are using that convenience an awful lot, right? So in part, we have this great technology that gives us a lot of these conveniences, and a lot of people are buying into it. We all are, right? And in terms of what are we doing? Like yesterday, I was a little bit lost in Mountain View. I got off the Caltrain stop for Mountain View. I'm like, okay, how do I get to North Bernardo Avenue? pull out my phone, bring on Google Maps. It located me, so it couples that with, let's say, GPS and whatever Google Wi-Fi in the area. And I navigated, I walked all the way to Toyota's office there. And that type of situational awareness, we didn't have like 10 years ago. What's the old school? And I still have that in my car, like these old maps. Oh, I'm lost. Pull out the big map of the United States, flip to Arkansas. Okay, I'm over here, right? Very different story than today. Okay. And the problem is, and this is where the problem is, society. Humans love this connectivity so much that we're beginning to gobble up spectrum in all shapes and form. And as a result, the original command and control mechanism for allocating spectrum is feeling sort of the stresses of this increasing demand. So this is a spectrum allocation chart that's produced by the NTIA. So that's the U.S. Department of Commerce organization that also deals with the issues involving spectrum. And as you can see, every colored blob here, from tens of hertz all the way to terahertz, represents an allocation. And as you can see, there's very few little white spaces to sort of allocate to new wireless applications. So what this graph shows is essentially we're running out of spaces where we can fit wireless signals to meet demand. Because imagine, I don't think people are going to decrease the amount of usage of their wireless. In fact, they're going to increase it, right? The more conveniences that are out there. And the same issue we see also in the UK. And also up north in land that's true and free, right? So in Canada as well. So and so what we're seeing is right across the board in most modern countries, we're seeing this sort of scarcity, but it's a apparent scarcity. And it's because it's command and control. The technology has outstripped legislation and policy in the sense that command and control worked when you had very static radio modules, but what happens when they become programmable and opportunistic? Now the regulators, and the FCC has been excellent at doing this, and others, in trying to keep up with the technology, but at the same time, two key issues. Making sure the technology works the way it does, right? Imagine you have a radio that is kind of flaky. You kind of programmed it the night before and then began jamming everyone, unintentionally, of course, right? That's bad, especially if it's something like, self-driving car. Like, oh yeah, there's no one there, and then you have a car accident, or worse, imagine it was a plane. At the same time, the second thing is the way we have to worry about legacy, right? So the spectrum allocations that are made, there are folks out there, cellular service providers, TV broadcasters. They've invested millions of dollars in creating that infrastructure. And what happens is all of a sudden, oh yeah, by the way, you're going to have these opportunistic folks squatting in your spectrum. They're terrified by that, especially if these guys that are sort of accessing their spectrum in a secondary manner provide services that rival their own. So there are some sort of policy issues that we got to worry about. But in this context, so here's a snapshot of Lawrence, Kansas, okay, of what spectrum looks like from 900 kilohertz to 1 gigahertz. And what you'll see is a lot of open space. So when we make these allocations to different entities, that's great. They have exclusive rights to them. But the problem is not so much sure, we got to respect those license rights to that spectrum, but what happens if they don't utilize it efficiently? So what's one community that doesn't utilize their spectrum all that much or even at all, but when they need it, they really, really need it? Any guesses? How about public safety? So, if there's no hurricanes, it's a nice sunny day or maybe cloudy day here, there's no problems whatsoever. Oh, it's great. It's like, you have, that spectrum's totally empty, and maybe we can use it for dynamic spectrum access. Maybe we can borrow that spectrum. But then let's say you have a hurricane. Let's say you have some sort of event or disaster. And then public safety officials and operations start picking up. And that spectrum begins getting occupied really quickly, right? And that's what we got to be concerned with is, how do we sort of balance sort of these legacy users, which have very specific needs, and they've invested a lot in their infrastructure and may not be adaptive or programmable or cognitive, and then couple it with our insatiable need to have more and more wireless connectivity. So keeping this in mind, where the engineering comes into this is essentially understanding that, first of all, there's going to be empty spectrum there and might not be efficiently utilized. Can we create technology that can access this spectrum in a manner that we respect those rights of the incumbents and make sure we don't interfere with them, and at the same time deliver, let's say, more wireless connectivity to meet the increasing demand that we've been seeing over the last decade? Okay? And this concept is called dynamic spectrum access, or DSA, where essentially what you do is you have secondary users. That's sort of like, these individuals that really want wireless access, and what we do is we fit them in wherever there is unoccupied spectrum in order to, let's say, perform that communications. Now I mentioned some of the issues, like what happens if a primary user, the person who has the license rights to that spectrum, suddenly shows up. Your radio has to be really fast. It's got to detect the presence of that guy and move out of its way, and in order to respect his rights. And let's say you're on a cell phone call with your mom. And that's not good either, because then if you don't somehow be able to, sort of readapt your network and establish a new link, you have a dropped call, and that's really annoying, right? Imagine, the number of times I'm talking and all of a sudden, zoom, my call drops. I don't want to call that person again. I probably would not want to subscribe to whoever's giving me that service. So dynamic spectrum access, the technical issues here is to create a radio platform that can readily adapt to an environment, take advantage of unused spectrum, and then whenever the primary user or the situation has changed, to readapt based on those conditions. Okay, and so software-defined radio, well, this is a block diagram, but it basically, the basic building blocks are here. You've got the software side, you've got your data sources, you've got your error correction, you've got your modulation, you've got your data compression. And so that, we can easily implement in algorithms, run them on a PC if you're using, the Capstone Communications Lab, or whatever software-defined radio platform you have. And then at the other hand, what happens is once we've got this sort of information all packaged up and ready to transmit over the air, we've got to bring it through the analog RF radio frequency front ends and send it over the air, exciting it at gigahertz of frequency. And so we have an RF front end, and traditionally, this has usually been not programmable, okay? So normally what happens is this side of the radio platform, we have the programmable nature. We can create new algorithms, new networking schemes and such, and then interface that with an analog RF front end. What it does is it takes the digital data, converts it into analog, brings it up to a new carrier frequency in the gigahertz range, and send it over the air, and then perform reception at the other end. And more and more researchers are actually looking at ways of maybe not making that RF front end programmable, but making it tunable. And so, first of all, here's some samples of software-defined radios. So probably a lot of you have seen this guy here, the USRP2, and that guy there is a custom-built, what we call a CubeSat, or a very compact form factor satellite software-defined radio that my group and I worked on an Air Force Research Lab project. We'll talk more about this later in the talk. But on the RF front end, let me go zoom over. There we go. So what happens is with the RF front end side of things, we take this chart. Suppose I'm transmitting at 88 megahertz, all right? So that's just the lower edge of the FM band. And I want to transmit now with the same RF front end at 5.8 gigahertz. Is that doable? Well, okay. So there's some products out there that are beginning to support that wider range. But let's say I want to even do a wider range, like across 20 gigahertz. What would I do in that case? Is it possible to do it with just one analog RF front end? And the answer is yes. So I know I'm jumping ahead of the gun, but I want to sort of add closer to this. It is possible, and the answer is with something called radio frequency microelectromechanical systems, or MEMS, RF MEMS. And all it is essentially is circuits such as the one here, like underneath this microscope, where you have, for instance, basic components like a capacitor or an inductor. And what happens is using electric fields, you can physically change the characteristic. Like let's say change the switching of this circuit. So let's say I want to connect to this part, like I want to create a new circuit. Some of those leafs would actually make contacts with other leaves and create a brand new circuit with different types of impedances and characteristics, and others would disconnect. And this is sort of one idea where you can actually support extremely wide frequency ranges of operation using a single RF front end. But the problem with this is the following. It's great because you can do things like create wonderful antennas or filters or oscillators, but very slow, on the order of seconds to adapt. So it's like, oh, wait a minute, I need to change a new frequency. And then, no. So not very practical. Okay, so now going back. So Joe Maitola, so he's kind of, one of his main claims to fame. So first of all, his PhD dissertation, wonderful read. You can freely access it down from the KTH website. It's the Royal Institute of Technology in Sweden. So he was the guy who coined the term cognitive radio. And so he worked for years at MITRE. He was a vice provost of research, I believe, at Stevens. And now I believe he's doing private consulting. Oops. There we go. And so this is what that vision of a cognitive radio is in a nutshell. So like with any radio system, what you've got is you've got the environmental stimuli. What's happening out there? Channel quality, signal quality, network load, desktop applications. What is happening out there? We usually refer to these as dials on the radio. Okay? And at the same time, you have knobs. You can adjust each one of these guys. Like let's say I want to change the transmit power, the packet size, the data rate, or any other sort of tunable type of parameters of this radio configuration. And then you might be constrained in terms of how many radios configurations you might be allowed. What sort of modulation schemes are you allowed having? What sort of forward error correction coding you might have? And then finally, the target network experiences, the metrics. What are we striving for? Low bit error rate, low power consumption, high transmission distance? What are we looking for? So all of these sort of contribute to what do you want, what do you see, what can you do, and what you can tune. So cognitive radio, in very much layman's terms, really comes down to being able to answer these questions with this platform in an autonomous manner. So the radio would actually be handling the tuning and the observing, and then taking these target metrics and allowable configurations to set up your radio for you in software. Okay, so we saw that. All right. So now, just a quick blurb about my lab. So this lab I founded when I got to WPI in 2007. Just in case you don't know where WPI is, if you've not been to Massachusetts before, you flew over it or something. So we're 45 minutes away from Boston, depending on how fast you drive, which is 45 miles. So it depends on traffic, too. If there's like rush hour, then it's a little longer than 45. So WPI is located in Worcester, Massachusetts, not Worcester, as I used to call it during my job interview there. And WPI is the third oldest U.S. Polytechnic. We're ranked 64th in the nation by U.S. News, as well as some other accolades like top 10 best colleges for young Einsteins and such. So what we are, our principle, our driving force behind our institution. So we're only like 3,800 students, both grad and undergrad. We have 220 faculty. So we're a very small college. But what our driving force is, especially by the founders, so Ichabod Washburn and John Boynton, is there's a theoretical component, and then it's reinforced by practical learning experiences. So, and that's been captured in our motto, which is German, Lehr und Kunst, which means through theory and skilled art or practice. And so, some snapshots. This is actually the electrical engineering building, and I was mentioning to Professor Arab Sahi, it is, I believe, still the oldest in-use ECE building in North America. Okay, so we used to do research on trolley cards, and there's one coming out of Atwater, Kent, and this is the addition to it. So now Atwater, Kent houses 318 undergraduate and 250 graduate students and 21 faculty, and we cover pretty much the range of ECE topics. And then Lehr und Kunst, theory and practice. A lot of our students at the undergraduate level do several project-based experiences that are requirements for their undergraduate education, including a lot of off-campus projects at places like Lincoln Lab, which is similar to like APL here, MITRE, General Dynamics, Silicon Valley, Wall Street, and other places. Okay? In my lab, I think I have to update the numbers, but it contains a lot of the software-defined radio platforms that is being used in the capstone communications course, as well as some antennas, MATLAB licenses, and other RF hardware. Okay? And sponsored by folks like NSF, Lincoln Lab, MathWorks, Air Force Research Lab, NRL, ONR, and a variety of other sponsors. Okay? So now on to the fun stuff, which is the technology. So I'm going to talk about two things. The first one is I talked about Agile. So one type of agility is spectral agility. Can I transmit in the frequency domain in such a way that I don't interfere with existing signals in the same or vicinity of the frequency, but I get my information across reliably? So and then the second topic will be a little bit more hardware-oriented, involving the CubeSats I was talking about. Okay? So dynamic spectrum access has another name for it, which is called opportunistic spectrum access. You can sort of seek out opportunities of empty spectrum and transmit across it, and that's great. But again, that issue, that policy issue, that the incumbent license holders, their rights need to be respected at all costs. So for instance, like DTV, digital television spectrum, is great, right? How many people here have seen a digital television signal on a spectrum analyzer before? Anybody? Okay, 1, 2. Okay. So it's a beautiful signal. It sticks out from the noise floor. It's 6 megahertz wide. It has a cute little spike on one side. That's the pilot. And you can see it clear as day. And you might say, okay, so any channel that's not being used, I can use for my own wireless transmission purposes, right? That's true, but how do you know? And how do you know that that spectrum is indeed empty? And even if it is empty, or maybe you can't hear it, maybe there is a person out there with rabbit ears, so their own digital TV antenna, and you inadvertently interfere with them. That's a no-no. The FCC would be coming after you and asking to cease and desist. Maybe that's actually a quick question. How many people here still look at TV, digital or otherwise, over the air? I'm trying to convince my wife that we should go digital because all of a sudden our cable provider began scrambling more channels. So this is not a good argument. Darn. Okay. So what happens is, what we've got to do is we've got to respect the rights of the incumbent license holders, but still facilitate this sort of dynamic spectrum access type of communication. So that's where the software-defined radio comes in. That's where opportunistic spectrum access comes in. So here's another snapshot. This is what Worcester's spectrum looks like from, let's see, 88 megahertz to 2.686 gigahertz. And what you see is you see some spiky energy signals. So these guys over here represent some sort of signal being present. And of course, there might be some signals that are like spread spectrum, so those are very difficult to find, or GPS and such. But theoretically, like, we have like a few well-pronounced signals and then potentially emptiness in between them all, right? So this here, like, how can we make more efficient use of the RF spectrum, which is a natural resource, just like water, just like oil, just like gold. So it's managed by the government. How do we access this and respect the incumbents, right? How do we do that? What we can do is something called the electrospace. And other than sounding really cool, what the electrospace is we can break down every wireless communication system into a variety of different dimensions. Spatial, frequency, temporal, maybe have diversity, and maybe a few other ways of orthogonalizing your transmission. Right? In this case, the most common ones are space, time, and frequency. And so what you want to do is, can we take advantage of the spatial separation between different users? Can we take advantage of the frequency separation between different transmissions? And the temporal aspect. I don't transmit now. I'm going to let this guy transmit, and then I'll transmit after him. Can I take advantage of all these dimensions and maybe other things like polarization, like CDMA, use a different code, and essentially have multiple folks overlaid with each other, but they each have a different code so they can be extracted? Can we come up with ways to transmit in the same vicinity and not interfere with anyone? And the answer is yes. There are several approaches. Things like cooperative communications, the cooperative approach for opportunistic spectrum access, where what happens is you have an AT&T or some sort of license, some license holder, and says, you can temporarily borrow my spectrum for 3 hours to do whatever you want and communicate your information. And then after 3 hours, I really need it back because that's rush hour and I need all that bandwidth. So the problem with this model, one of several, is you now put the onus on this legacy guy that might not have the infrastructure or the equipment to facilitate this sort of negotiation. And that's great, but now he has to invest more, and he might ask, why should I share? I've got exclusive rights anyway. Who's going to force me, right? Or how much are you willing to pay for it, right? The second guy, the underlay approach, I like to say it's like flying below the radar. If they don't hear me, maybe I won't get caught, right? So ultra-wideband communications, transmit your information at such a low power, like for instance, like NFC, near-field communications. So only a device extremely close by can hear you, and you're not interfering with anybody nearby. That might be an option. And then last but not least is the overlay approach, which I'll illustrate right now. So again, we go back to our frequency spectrum of Worcester, and then the underlay approach is essentially transmit below the radar. Transmit at such a low power, at a very close distance, get your signal across, and hopefully the primary users don't hear you, all right? But that, unfortunately, also increases the noise floor, and there are a variety of other issues that make this option a little bit tricky to implement, especially if the receiver's like, hey, is someone transmitting? Okay. The other approach, the overlay approach, is to take advantage of the unused portions of spectrum and transmit your signal down those, what we call spectrum white spaces or spectrum holes. And you can do that, and one waveform that's really nice is multi-carrier modulation. And why is multi-carrier modulation so nice, especially things like orthogonal frequency division multiplexing or OFDM? Because it has a divide and conquer approach. You take this nice bandwidth, you split it up into lots of narrow slivers of low data rate transmissions, and then at the receiver, all those slow transmissions get multiplexed together to a single high-speed data transmission. It's used in Wi-Fi, WiMAX, 4G, 3G. It's used extensively in a lot of wireless communications, especially for data applications, because it has this divide and conquer philosophy, which is great for things like treating the signal at the receiver. So multi-carrier modulation can be perceived as having, let's say, your transmission actually consists of many very slow narrowband transmissions all clumped together, like how I illustrate here. Like the red here would be one transmission, the green would be another transmission, the blue and purple would be yet another. And notice that they all consist of lots of very narrowband transmissions all being transmitted at the same time. What's really interesting is here. So let's zoom in. What happens is, instead of having one contiguous block of these little narrowband transmissions, I've noticed that there might be a user in the middle of that spectrum. Let's deactivate a few subcarriers just to make sure we don't interfere with what could potentially be a licensed user. So what I do is I have an aggregation of all these narrowband transmissions, and then I turn off a few in order to ensure I don't interfere with what could potentially be a primary user. And then to implement it, like this is one sort of implementation, and this graph is from a paper that appeared last year in collaboration with some folks at Poznan University in Poznan, Poland. The way it works is you take your high-speed information and you decompose it into these narrowband subband or subcarrier transmissions, and then they get multiplexed together before being sent out over the channel. And then the reverse operation occurs at the receiver. And so the big problem occurs here with these gammas. These gamma 1s, 2s, all the way to m-1 and the G1, G2. Those analysis and synthesis filter banks. So what does industry use? What does Wi-Fi use? What do a lot of people use? They use essentially sync pulses in the frequency domain to sort of shape each one of these subcarriers. What's the problem with a sync pulse? Very high out-of-band emissions. That's bad. So if you're trying to transmit in frequency and you have a signal next to you It's almost like, let's say I'm sitting down over here, and all of a sudden, for some reason I'm talking too loudly. The gentleman next to me wouldn't be able to either pay attention to the talk or anything like that matter, right? So the worry is that OFDM, in particular, has all these out-of-band emissions, and this is bad news if you're trying to prevent interference with other signals. So it looks kind of like that mathematical, if you take the exact expression for a sync pulse, essentially you have your main lobe, and then you have all these side lobes, and they don't decay fast enough to enable sort of transmission right next to a licensed user, because it will interfere with him. And imagine if you have a bunch of them. They constructively combine, and it gets even worse. So there are several solutions out there. There's carrier cancellation. There's modulated filter banks. You can combine the two together. So what you can do is, I mentioned constructive combination. You can also insert, with the right amplitude and phase, these dummy subcarriers on either side of your OFDM transmission such that they cancel out. They combine destructively with those out-of-band emissions. So we call this cancellation carriers. You can also filter using things like a raised cosine or other sort of filter, and you can attenuate the out-of-band emissions, but this also introduces a slew of implementation issues when it comes to real-world hardware. So what we did is, both at Poznan University of Technology as well as at WPI, what we did is using USRP hardware, we created spectrally agile waveforms using cancellation carriers and using filter bank approaches in order to do the out-of-band rejection. And what we see is, first of all, this is sort of actually, this is not a great plot. This one's actually, which was published, is a little bit better. So the light blue curve here is the theoretical spectrally agile waveform. So imagine in these notches, you have a licensed user, you have a licensed user, you have a licensed user. Maybe you have licensed users on either side, and you want to transmit around them. So what do? You turn off the subcarriers. Now, what happens is you turn off your subcarriers, and at the same time, what you want to do is, let's say, use some cancellation carriers to ensure that your attenuation in these stop band regions is sufficiently low that you don't interfere too much with your licensed users. And what we have here is an illustration of when we use actual hardware. So the black curve represents actual hardware utilization using the USRPs. What we get is a very close match with the theoretical results with cancellation carriers and windowing up to a certain level, and that's pretty much where the interference and noise floor is. So we have just the noise floor here represented in green, and if you don't do anything with cancellation carriers or windowing or whatnot, that red curve is what you get. A lot more interference out of band. That's bad. Okay, so I'm going to wrap things up with some cute pictures of what is a CubeSat. So when my sponsor from the Air Force Research Lab in Albuquerque, New Mexico came one day, and he brought this little box. It was about this tall, it was about this wide, and it was about this thick. And he says, hey, can you build a radio? And I say, it's going to be a little tight to fit in that package. And he says, no, you don't get it. This is the satellite. Your radio is supposed to fit at the bottom of it. And I'm like, okay, how do you do that? And what the Air Force Research Lab is very interested in is creating these satellites based on really inexpensive technology. They don't want anything radiation-hardened FPGAs because it's too expensive. The development time takes too long. What they want instead to do is essentially have some sort of disposable, cheap, small software satellite payload, so-called CubeSats. You would have hundreds of these. They would go on a rocket. They would be dispersed, and then you can do advanced sort of communications in space. Let's say you can do beam forming or measure space weather, which is sort of the charging of the ionosphere and whatnot, or even like surveillance. You all have these cameras, and then all the images are fused together and launched on a single rocket, put in space, a few hundred satellites, perfect. How do you design a radio to fit there? So really, the key is, what we did is we took the predecessor to the USRP2, the USRP1, and respun it to fit in that form factor. And so it had a FPGA, a Spartan 3A. It had some custom hardware. And we also worked with a spin-off company at the University of New Mexico called Cosmiac. And what we wanted is to create an adaptive communication system payload for a CubeSat. And so what it looks like, and no, the bottom, that's the end of the CubeSat, is about 3 inches by 3 inches. It's very small, right? If you've seen in the Capstone Communications Lab, the radios are actually quite large. This is actually a really compact form factor. So can you put all that programmable functionality into a small payload like that? And the answer is absolutely yes. So this is what the folks at Cosmiac constructed. And what they needed now was all sort of the software, firmware, and interfaces to, so the firmware and as well as interfaces to, let's say, a software-defined radio software architecture like GNU Radio to run on top of that. And so that's where my PhD student, Steve Olivieri, came in. And this was published in ICC in 2012. What happens is at the core of all this, you would have a Spartan 3A FPGA platform, and you would have a collection of other interfaces as well as connections to the rest of the satellite payload as well as its resources. And what Steve did is he basically created the firmware surrounding a microblaze, which acted like a microprocessor on that FPGA to run most of the operations of that platform. And so how do you test a CubeSat if you don't have, let's say, financial resources to launch it in space? You just hang it off the side of a very tall building. So Albuquerque, I think it's like 350 days out of every 365 days a year, it's like this. It's always blue, blue, blue skies. This was at Cosmiac's location in Albuquerque, New Mexico. We would hang the radio off, and then with the Cosmiac base station, we would facilitate communications and see if it would work. All right? Okay. So in case you would like to know more, my email address, thank goodness, I chose Alex W. rather than A. Wyglinski because I probably would not receive half the emails that would be sent to me. Law of information can be found at my lab website as well. It needs to be updated, but it's relatively current in terms of wireless.wpi.edu. Professor Arab Sahi also mentioned about my books. So this one came out in 2009. At the end of 2009, it's an edited book, of which I think a quarter of it was written by myself and my students. But it basically experts in the area of cognitive radio and dynamic spectrum access. A great book if you want to learn more about cognitive radio. This is the book that's being used this semester here. And if you want to access to the source code or the freely available lab guides, there's also a website for that, which is str.wpi.edu. And so that came out in just this year. It's on Amazon. And my PhD student, Deepu, she just defended her PhD last week, and I co-wrote it. So it was a very busy summer last year. So with that, I would like to thank you again for your time, and I would be happy to answer any questions. Thank you.
I think we have time for maybe one question.
You just touched on ultra-wideband in passing.
Yep.
Isn't our preoccupation with bandwidth a function of the fact that we didn't have broadband and high-speed processors, and now that we do have broadband and high-speed processors, wouldn't one naturally eventually migrate towards ultra-wideband structures of communication?
That's a great question. So essentially, given the advent of the latest technology in terms of broadband and communications technology, is ultra-wideband a viable option? And the answer is it depends on the application. The reason why I sort of shied away from things like ultra-wideband in this research is mainly because if you have, let's say, numerous ultra-wideband transmitters, you have the potential also to increase the interference floor of your spectrum. So on the one hand, if it's just you and you have a very wide bandwidth, that's great. But if you, let's say, support an entire network of ultra-wideband transmitters, now what you've got is sort of like all of these guys are going to be summing up together, creating that interference model. Whereas the overlay approach is tricky in the other regard, in the sense that you have to have a lot of knowledge of where your existing transmitters are. But once you know where the holes are, you can transmit around them and not really worry about increasing any interference level, except for the fact that if your waveform is not sufficiently band limited, you just like the out-of-band emissions, you have that problem. But yeah, one friend of mine, Zichang Wu at Wright State University, he looked at a hybrid solution. So what he did is he had the overlay, And wherever there was occupied spectrum, he would do an underlay on it. So he sort of like went all out. He tried to transmit in both modes, and he's published extensively. One of his PhD students that did that work, actually, she graduated. She actually gave an invited talk at WPI about a month ago. She's at Western New England College right now in Springfield, Mass. So yeah, so it's a very interesting concept. It's like you have, the funny thing about this area is that there are multiple camps. So there's ultra-wideband and the underlay folks versus the overlay. Even multi-carrier, there are folks that say, OFDM is the best and I'm going to stick with it. There are others that say filter bank is the way to go. Why do OFDM and stuff? And I think in the end, it's how you, what application and how you package it that really matters. So that's a great question. Thank you. Any other questions?
Thank you again. Thank you, Alex.
Thank you.
Thank you.